Okay, so now we will start the second chapter. This is actually our last chapter today. Although we have supposed to have three classes today, we're not gonna really have three classes today. I will move one classes into the future because you guys have already learned too fast. So I don't want to test that much stuff in the first midterm, which will come at the end of next week, end of this month. Okay, so let's do the chapter 6, decision making under uncertainty. So suppose you are facing such a decision, you're gonna decide between you're gonna produce one batch or produce two batches for the food manufacturer for a food manufacturer to make this decision. So if you make one batch, but the demand for the number of batches is only one, then you match it, then you earn $200. But if the demand actually two batches, you cannot match the second batch, so you also earn only 200. And if you make two batches and the demand is actually only one, that means you basically waste one batch, so you lose 600. But if you actually meet the demand, you will win 400. So what would you do? Do you risk making two batches to have the chance of winning 400, but risk to lose 600, or you will simply produce one batch to win $200 for sure? So if you use something called the max min criteria, that means you maximize the mean, the maximize the lowest possible payoff. So if you produce one batch, the lowest possible payoff is gonna be $200. If you produce two batches, the lowest possible number is minus 600. You want to maximize between the mean, so this is greater than that. So the maximized number is $200. So that's why you're gonna choose to produce one batch. Okay, so you, we we choose the action that maximizes the mean. Right, so we choose produce one batch. Okay. Um, Another criteria is called the expected monetary value criterion, which is the called EMV. It basically, so this one requires the idea of expected payoff. Okay, so we have learned the expected value just now, right? So we need the probability. That's the probability. Okay, so this is PI, this is PI, this is PI. This this is basically XI. Sorry, this is XI. This is action. So this is action A, action B. Okay. So if you do action A, the XI times PI plus XI, PI times XI gives you 200. So the EMV is 200. And if you do the if you produce two batches, it's gonna be 0.3 times this minus 600, 0.7 plus time 0.7 times 400, which is this, and it's equal to 100. So now this is greater than that. So the EMV of produce just one batch is greater than so produce one batch is better than produce two batch. That's the EMV criterion. Okay, and for the EMV criterion, we can also run a sensitivity analysis, which I already told you last time that we will do a lot of these sensitivity analysis, right? So the only variable here is so xi is fixed, right? Xi is fixed. So the only variable that you can sort of vary is pi. Now you have pi is 0.3, 0.7. 0.3, 0.7 is actually here. The probability of equal to one batch, right? Probability of demand equal to one batch is 0.3. In this case, you can see that the height for this one is the, you know, the this line. This line is the EMV of produce one batch. And this other line, let's use red. This other line is the EMV for two batches. Okay, so you can see that when the probability is 0.3, it is true that produce one batch is higher than the yellow line is higher than the red line. And that's why you said that produce one batch is better. And that these two lines are intersect at zero point 0.2. What that means is when probability is 0.2, two actions are equally good. Okay, in terms of the EMV criteria, only under EMV criteria, okay, they are equally good. Okay, so if the probability is greater than zero point 0.2, produce one batch is better. If the probability is lower than one batch, zero point 0.2, then produce one batch is actually worse. Produce two batches better under this criteria. So the sensitivity analysis can tell you if you're not sure exactly about the probability and it's actually quite close to zero point 0.2, then you might think either way, the expected monetary value is the same. Okay, so there are some limitation of the EMV criteria. Okay, he assumed that the decision maker is something called neutral to risk. It means that I don't care about the risk that much. So if there are two options, option A and option B, the EMV of A and EMV of B are equal, but A has, we'll define this later, but higher risk. This one has, lower risk. For for you to use the EMV, this person who used EMV, uh, option A and B are equally good because of this equal sign. That means they're neutral to risk. But usually people are risk averse. They don't want risk. So the lower risk one, option B, will win. Okay, and the second one is that it assumes a linear value function. Actually, as we will see later, these two are equal. These two are equal. Okay, and also because we are talking about expected monetary value, right? It's monetary, so we only care about one attribute, which is money, and we might want to care about more than that one attribute, right? Okay, and now now let's look at the risk attitude and the curvature. So of the utility function. Okay, so what is the utility function? Um, so utility function. So what is the utility function? Basically, the x-axis here is money, and the y-axis here is utility. Utility. Okay, and you should have learned this in microeconomic course. Okay, so suppose we assume that if you has no money, you have zero utility. Then you start with this point. And if you have a lot of money, say 1 million, and you will have a lot of utility. Okay, say this is 1,000 in terms of utility. Then this is on your utility function, and we usually assume that utility. So if suppose your utility function looks like this we call concave. remember from last time, we were talking about value function. This is close to the idea of value function, okay, but different. Now, uh, what is the underlying assumption of this concave utility function? Let's first draw a straight line connecting. Not very good. Okay, so um, this actually means that this person is risk averse. And why is that the case? So let's look at any two number. Um, okay, so this is x1, this is x2. Okay, this is y1, uh, this is y1, this is y2. And uh, let me draw the concavity a little bit more um, obvious. Actually, I'm gonna redraw this. This is not that obvious now. Okay, and so okay, so suppose it's here and here, y2. Okay, and or if we take this and take a take a we take a deeper look, then it looks like this. This is the straight line, and this is the utility function. Okay, so what you can see now, what this means is if you have the amount of money you have is x1, you have y1 utility. And if the utility that if the amount of money you have is x2, then you have y2 utility, right? And if I give you something in between, that's x1 plus x2 divided by 2, so you have u of x1 plus x2 divided by 2. By definition, by this curve, you will see that you will get here. You will get this amount of utility. Say this is A, then this is equal to A. But what is this length, this B? Remember, this is a straight line. So this B will equal to u of x1 plus u of x2 divided by 2. Okay, this is high school math. Okay, so and you can now see that in this case, A is greater than B. A is greater than B. What this means is if there's say half chance, if there's a half chance you get x1, another half chance you get x2, okay, then this is the expected, uh, this this is your EMV, right? But and what is this? This is B, right? What is A? A is exactly I give you x1 plus x2 divided by 2. So you don't have a half chance getting a higher number, lower number, not a half chance getting a higher number. You just get x1 plus x2, the average of these two numbers for sure. So you'd rather get it for sure, but you don't want this EMV. This is not EMV, sorry. This is the called expected utility. Okay, expected utility. But um, this is so you rather will get this for sure. You don't want to have a half chance getting one and the other. Okay, so that means you are risk uh, averse. You don't want risk. You want something for sure. Okay, because these 2 points, the EMV is actually the same. Okay, because half chance getting this, half chance getting that. The EMV is half x1 plus half x2. Is exactly 1 over x1 plus x2 over 2, right? So the EMV of these 2 points are the same, but you prefer having the fixed one. That's why. So with the same EMV, you want the lower risk one. So when the utility curve are concave, that means you are risk averse. Okay. And similarly, uh, if you have something like this, that means you're uh, risk prone or you're risk loving. Okay, I like the word loving better. Risk loving. And if you are the straight line, exactly the straight line, that's exactly what I would already say. This is risk neutrality. And if you are concave, as I already said in the previous slide, you are risk averse. Okay, so um, so for the first example, the whether you want to produce one batch or two batch, if you're gonna use the utility function method to find the optimal strategy or optimal choice, you should first find the utility function. And this you can still use the bisection method that we talked about in value function chapter, right? So uh, there's actually a chance of you suppose you find that the if you got minus 1,000, 10,000, the utility is 0, and you find that if you have 60,000, your utility is 1. This is 0. This is 1. Then you want to use the bisection method to find something around, you know, what is this number, and then further find what is that, what is the 70 0.25, 0.75, this is zero point 0.5, and you find the corresponding number, then you draw the line like this. Okay, the bisection method we talked about last time. Okay, after you have found the utility function, though, this becomes really simple. Okay, you simply so we actually have a different example now. The decision tree, this is for a conference organizer. You're gonna either choose a luxury hotel. You're gonna either choose a luxury hotel, you choose a Maxima Center, and you might get high attendance or low attendance, high attendance and low attendance. I use different color better. High attendance and low attendance. Okay, and then you simply write off this probability, this number. Use your utility function. You get u of 30,000. This u of 11,000. This to u of 60,000. This to u of minus 10,000, which gives you 0.85, 0.6, 1, and 0. And the expected utility. So as the name suggested, what is the expected utility? Now it's not the expected money, but expected utility. So it's zero point 0.6 times 0.85, zero point 0.4 times zero point 0.6, and you add them together. This gives you 0.75. That's this number. So the expected utility you do from choosing a luxury hotel is 0.75, and the expected utility you choose from the maximum center, that is calculated by zero point 0.5 times 1, zero point 0.5 times 0. This one is easier to calculate. So 0.5 times 1, this is 0.5. 0.5 times 0 is 0. And these two add up together is 0.5. So the expected utility is 0.5. And you can see that since this one is 0.75 is larger, so you will choose the luxury hotel. What I have done here is show how to use the expected utility to decide what to choose. Expected utility does not equal expected money or monetary value. Okay, that's the key because we use a utility function. We don't, and this is not linear. Okay, that's the key. And um, utility function can also be defined something other than money. Okay, so actually I wrote it here. Money is not the only attribute that can be entered in the utility function. For example, here is the development time. We know that, so this is the years that will enter the utility function. We know that, for example, this utility function means that if I wait for 8 years, suppose I'm develop some new technology, and if for example, or develop develop a vaccine for the coronavirus, and if I wait for the development time is 8 years, then there's no value because everybody already died. Okay, so 8 years too long, the utility is 0. And if I somehow can develop the vaccine within 1 year, then the utility is really high. Okay, and you draw. So you also notice that if you have 2 years, it's also really high. 4 years is not that high. So you connect these dots and you find the utility function for this guy. And notice that for this guy, his utility function for the development time is also concave, because if you connect this line, you can see that this is still the straight line is below the curved line. That means this person would rather have a fixed development time other than a random development time that has the same expected year. Okay, so again, this is very simple. So um, if the two action that you can take here is continue with existing model or switch to a new approach, then the drug company is doing using these two methods. And if you do so, there is a 40% chance the development time is 6 years, 60% chance that it will be 4 years. And here is these three cases. How do you do? You simply convert the year into utility. You use you know utility of 6 years. Okay, then this gives you zero point 0.5. So you write off this as 0.5. Similarly, if it's 4 years, utility is 0.75. We know that if it's 1 year, utility is maximized. If it's 8 years, utility is 0. If it's 2 years, utility is 0.95. And within, this times this, this times this, this times this, summation together, it gives you 0.85. And here, zero point 0.4 times 0.5 equals to 0.2, right? And 0.6 times 0.75 equal to 0.45. Okay, so and 0.2 plus 0.45 equals to 0.65, which gives you this. So the expected utility of continue with the existing model is 0.65. The other one is 0.85. So this one is bigger than that one. So we're gonna choose to continue with existing method. Okay. So the expected utility method can be used in context other than money as well. Okay. But there are some limitation to the expected utility criterion. The first one we actually show you uh, in the experiment that we run in the first week. Okay, we actually talk about this in the second week. Remember this, the alias paradox. So there were two lottery, right? So lottery A and lottery B here, lottery C and lottery D. Remember, I told you that if you are perfectly rational, then you should either choose A and the C, or you choose B and D. We talked about this last time. But actually, a lot of people choose A, D, or B, C. And that actually means there's one axiom or one assumption in the expected utility criterion has been violated. We will talk right after this, shortly after this. Okay, and we'll see why it's violated. Okay, so um, there's are actually four different axioms for the utility expected utility theorem. Okay, this is actually developed by a very famous economist and mathematician, von Neumann, who also joined the project in the U.S. to create uh, the 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 atom bomb that dropped in Japan. Okay, so what are these four assumptions? The first one is completeness. That simply means if you compare two lottery, L and M, either I will like L better than M or equally good, or the opposite. I will like M better than L. Okay? Either one of these is gonna happen. If both of them happen, that means L is equally good as L. But if either this one, or this one, three of these gonna happen for sure. The second one we saw this before is called transitivity. If I like L better than M, M better than N, then I will like L better than N. The third one is continuity. So if N is something in between L and N, then we can find a probability that is between 0 and 1, such that a combination, a mixed lottery of, you have a p of chance of p getting L, 1 minus p of chance getting N, it will be equally good as M. So this is like I have a big reward, a small reward, and something medium. Then the mix between the big and small, some kind of mix, one p and 1 minus p mix will be exactly equal to the mid option. Okay? Um, the third one, the last one is the most important one, most easily validated one. Actually, in this example, the alias paradox one, this you only need this one to be violated for you to choose A and D and or B and C. Okay, and this stated that for any p, this is not for a specific p. Okay, for any p between 0 and 1, not include 0, if L is better than M, okay, if we already know that L is better than M, that implies if now I give you a chance of probability P getting L, probability of P getting M, and then the same thing, sorry, a probability of 1 minus p getting in, also 1 minus probability getting in. Because these two are the same, right? It seems like we can write off this too. It doesn't matter. We're gonna get a 1 minus p chance getting the n anyway. We shouldn't care about that part. And since we shouldn't care about that part, then the rest is a probability of p getting L, probability of p getting M. The probability shouldn't matter, right? So that's why this assumption is somewhat rational, right? It suggests a rational idea. But you can see here in the alias paradox, we are exactly doing this. This part is exactly the same. We only differ this part. So we shouldn't care about, sorry. So we shouldn't care about this part, which are the same, right? And this one, this one, you know, this one is just 1 million higher than this one, but this is, no matter what's the probability, it's gonna be 1 million higher. So that's why we should have a consistent preference, saying I either choose A and the C or B and the D. But if I'm not doing that, that means I have violated this one. That means including something that's irrelevant would change my preference. Okay, this L and M are like the lottery A and lottery B in the previous slide, and this new thing is like C and D. So if I like A better than B, I should have liked C better than B. But if I'm not doing that, that means I violated this independence of irrelevant alternatives. Okay? Now we have already finished everything about a single attribute utility. Now we're going to talk about a multi-attribute utility model. Okay, so uh, in this case, what is multi-attribute? Actually, quite simple. So this is a decision tree for a project manager's project problem. So if this project manager is deciding on work normally or hire extra labor, if you this guy work normally, he has a 10% chance that have an overrun time of 0 week, and the project gonna cost him 50,000. So these are the two dimension, two attributes. Okay, so attribute one is time. Second attribute is money, basically. And if there's another 60% chance, the overrun time is gonna be 3 weeks, and the cost is gonna be 60,000, and so on. So the problem is that we don't have a utility function that deal with two dimension. Okay, we can have a utility function for money, a utility function for overrun time. This is money, this is time, but we don't have one for both. So how do we deal with this? To deal with this, we first need to have something called the utility independence assumption. What is utility independence? So we say that attribute A is utility independent of attribute B if basically, how should I say this? So, uh, if I'm asking you with different level of asking you choose between different level of A, but same level of B, then I don't care about the B because it's the same level of B. I should only care about the amount of A. If that's true, then A and B are independent. How do you test this? You should ask the decision maker or yourself the following question. Okay, the question is something like this. So, um, this lottery A has sorry, lottery A here has a 100% chance of one having an overrun time of 2 weeks, and the cost is gonna be 50,000. And if you choose the option B, there's a 50% chance of getting the best overrun and with the same cost, and the worst overrun and by the same cost. And the second one, you simply alter the number here. Um, let's use a different number, a different color. So the only difference you see is here. Is the red in the red color is 50,000. Here is 140,000. If you only change this number, I should either choose A and C or choose B and D. So in if you ask me to choose between A and B, I should choose. If I choose A, I should also choose C here. If I do that, then that means I don't care about this cost part. The cost vary with different level of cost. My decisions are still consistent. Okay, if that's true, then I can say that I am I have this utility independence. Okay, so if you test this and you find that it has a utility independence, then I can have two different utility functions, one for overrun time and one for the cost. And this we have already talked about this. This is for the money, this is for the time. And um, so suppose the utility function is given as follows. This is the overrun times utility, different level of utility, and this is the cost project utility. Then the utility for this multi-attribute utility function, the total utility of x1 and x2, this is maybe money and this is time, is basically the first utility function, the second utility function, and a weighted average between them. And then a third part is the multiplication multiplication of these two utility functions with third uh, a third weight in front. We have a restriction. This is very important. K1 plus K2 plus K3 must equal to 1. So if I know how to decide K1 and decide K2, for example, if K1 is zero point 0.1, K2 is 0.5, then I will know that K3, sorry, K3 is 0.4. Okay, so how do I decide K1? So we're gonna ask a following question. So I will ask this the individual, the decision maker, to choose between these two lottery. The first lottery is the best possible overrun and worst possible cost with 100% chance. And then the second lottery is a best overrun versus the best cost, and the worst overrun versus the worst cost. And I ask about the probability of K1 that makes lottery A and lottery B equal. So a way to ask this question is, say, for example, if K1 is 1, that means for sure I will get the best outrun and overrun and best cost. In this case, if K equals to 1, I know B is better than A. If it's K1 is equal to 0, means it's gonna happen is the worst overrun weeks and the worst costs, then I know for sure A is greater than B. So there must be something in between 1 and 0, for example, maybe 0.6, that makes this individual indifferent between lottery A and lottery B. You can start with 1 and go down by 0.9, 0.8, all the way to 0 and find the number that this person feel most indifferent. Then if you find that number, that's K1. Similarly, you can use a different setting like this one to find the K2. After you find K1 and K2, you will be able to find K3, remember? So now, for a multi-attribute utility function, a utility function that has two attributes, you will be able to convert 0 week and 50,000 project costs into one utility. 3 weeks and 60,000 costs into one utility, and so on. Then you can calculate the expected utility as well, and just compare the expected utility. You know this one is greater than that. Then you know what to do. Okay. So actually, we have basically finished today's class. Um, so remember that we said in the beginning of this semester that we will have some assignment, right? So basically, this is this week's assignment. So for this is all referring to your textbook. Okay, so chapter 2, you should do the DQ. That means the discuss question number 2. And for the chapter 3, 4, 5, 6, you should do the following exercise. This is exercise. EX stands for exercise. Okay, so these are the questions. I know it's quite a lot, but that's because you guys got the textbook a little bit later. So, but remember, the point of these assignment is not to challenge you. It's really to let you practice. So don't be afraid of writing too much assignment. Okay, and remember our rules is that you should hand in the assignment next week on the during the class in the beginning of the class. The TA will come into the class and collect the assignment for only 10 minutes. Okay, and the TA we have for this class is Wu Yishen. Okay, so Wu Yishen, her email is this bb3419@gmail.com. If you want to hand in the assignment electronically, then you should simply send to the this email. But the deadline is the same. Okay, so you should send the email 10 minutes before 10 minutes after the class, before that time. Okay, and one thing is that um, so there's a reminder, we will have the midterm uh, on the end of this month. And I told you in the beginning of the semester that uh, next week will be no class, but actually, because I canceled the my conference trip next week, so we will actually still have the class. But like I said, I already taught too much before the midterm, so the midterm is gonna test you the idea from chapter 1 to chapter 6. We won't teach anything new next week. We will actually discuss the assignment next week to make sure that you understand all the assignment questions. Okay, so that's it. Thank you.